Hello everyone, welcome back to my channel. So in this video, I'm going to be going through this problem of fluid mechanics. In this problem, the tank shown below is partially filled with a liquid of density rho and is open to the atmosphere. A triangular gate is hinged at the bottom and held closed by a force applied to the top. Determine the force F in terms of the liquid density rho, the acceleration due to gravity g, the liquid depth d, the gate height h, and the gate width w. So, this is first we have to begin with our force equilibrium and moment equilibrium equations. So, the moment must be equal to zero since no water is pouring out. So the moment about the hinge must be equal to zero. And what are the moments? So the force over here will exert a moment um about the hinge at a distance of h. So we know that we have one moment, and this moment is going to be counterclockwise, so it's going to be positive, so we have FH. The other moment will come from the pressure force on the gate, and this pressure force is caused by the hydrostatic pressure of the liquid with the density rho. But however, how can we express the moment caused by this hydrostatic pressure? This is a tricky question because the gate is an irregular shape, and thus the pressure force will vary according to the height and the shape of the gate at each location. It's helpful to first draw a side view of the setup. So if we look from this direction, and let's call it the YZ direction, where let's call it the Z direction actually, and let's call this one Y the YX direction, so XY. And so this one will be YZ direction. We're basically turning the whole setup. So in the YZ direction, the diagram will look something like this. So you have our gate, we have water up to a certain height, and water up to a depth of D. This is the flow. This is the floor. And this water pressure varies like so, linearly. And the force is applied at the top, just over here. This is the force and the height, h. Mm-hmm. And so in the yx direction, we have this triangular shape. And this is the yx direction. The width of the gate is actually W. And we have to integrate because the pressure varies over the surface of the gate and the gate width changes with depth. So we'll need to integrate the pressure force over the gate surface. So in order to do this, we have to divide the gate into small areas over which the pressure remains constant. Because as you will remember, pressure is equal to force divided by area. And although the pressure varies linearly on the water as a function of depth, the area changes, and thus the force exerted on the gate will be different at each location since the area here is not the same as the area here because of how because of the gate's geometry. So we'll need to divide the triangular gate into sections of small areas over which the pressure remains constant. To best do this, we can divide it into strips. And divide the gate into strips. And each differential height will be dy. And each distance of the area from the bottom will be at a distance of y. And we will have to find what the differential area is, which we will call dA. So we have to come up with an equation for dA in terms of dy. Because we want to get everything in terms of only one variable, which is in terms of y. So how do we go about doing that? We notice that this differential area is like a little rectangle. So we're dividing this triangle into little rectangular areas with height of dy and a certain width. Now we have to come up with an expression for the value of this width as a function of y. And the way we do that is we consider the equation of a line. As we see over here, we have a triangle with this total width is w. We want to find the equation of this line first of all. And once we find the equation of that line, it will give us an expression of the x, which is the horizontal distance in terms of y. And then we would then multiply that by 2 in order to get the whole width over here. And why this makes sense is because of what an equation of a line represents. So basically, if we find the equation of a line, like maybe for the right side of the triangle, we find it for this line, but it will only give us half of the horizontal distance. So we multiply it by 2 in order to get this whole distance. So this whole distance will be called 2x. And it will give us the value at each of these points. So equation of a line, what do we need? We need the slope, and we also need a constant. So what is the slope? Well, the slope is going to be rise over run. So the equation of a line in general is y equals mx plus c. And m is the slope. And slope is rise over run. So as you see, the gate has a height of h and a width of w. However, we want to find the equation of this line over here. So the width will actually be w over 2. So we'll be using w over 2. The slope is h over w divided by 2. So y equals h divided by w divided by 2, which is 2h over w x. And then what is our constant? The constant value, actually, let's backtrack a little bit. Let's make it more explicit that we're actually finding the width as a function of y. So let's call that equation wy. And And Wy is equal to my plus c, and c is some constant value. Now we still have to find m, which is the slope. So we will use Wy minus Wh over 0 minus h. And what this means is we want to find the width, the width when y is yes. So we want to find the width when it is at y. And wait, sorry. So actually I mean like W0. Yeah. So at y equals 0, the width is actually W. And at y equals h, which is over here, the width is actually 0. So we will have W minus 0 over 0 minus h, which will give us a slope of negative W over h. And so from the equation of a line, Wy is equal to negative W over h, y plus c. And the c is the value of the width at y equals 0. That is what the c in that case means. It is when at y equals 0, the width is equal to W. So we will add a W over here. Because at y equals 0, the width is W on this gate. And we can factor out a W to have W 1 minus y over h. Okay, so now we have an expression for the width as a function of y. And our differential area A can be now expressed as this width multiplied by dy. Because over here, the differential element was actually with a height of dy and a width of wy. That's why we do dA, and this is dA. So dA is equal to wy multiplied by dy. All right. So what is what is the differential force on each strip? That is what we want to find. So the differential force, which we will call dF, is equal to the pressure times the area, because pressure is equal to force divided by area. So a force would be equal to pressure times area. And this is equal to Py times Wy times dy, which is Py times dA. And Py is the hydrostatic pressure as a function of height. So as a function of height, Py is equal to rho times g, and rho is the density of the liquid, and then g is gravity, multiplied by basically the depth. And the depth of the water on the gate can be represented as d minus y, where y is some distance up the gate, so d minus y will be this distance over here. So if we are looking for a pressure at this point, we will do d minus y, and this point is located at a distance of y from the bottom of the bottom of the whole tank. So y is the distance from the point from the bottom of the tank, and d minus y is the depth of the water at that point. That is why the hydrostatic pressure is expressed as rho times g times d minus y. Yes. So then we have that this is equal to rho times g times d minus y. And then wy is times w1 minus y over h, and then times dy. And basically, since the total hydrostatic moment is equal to m, is equal to force times the arm length, in a general form, this can be represented as the sum of the moment across the surface of the triangular gate is equal to the integral of y times df. So basically, how this makes sense is because y is the distance from the bottom of the tank to the differential area. And basically, moment is equal to force times the arm length. And this water is trying to push on the surface of this gate at a distance of y. Basically, the force is acting at a distance of y. And the force comes from this hydrostatic pressure. And the hydrostatic pressure is related to the area, as we found over here. And the differential forces equation is this one, which we got all in terms of y. So now all that remains is to first find the lower and upper bounds. So we're integrating from 0, which is the bottom of the tank, to d, which is the top of the water, not the water, but the liquid surface. So integrate from 0 to d of y df, and this will give us integral from 0 to d of rho g d minus y w 1 minus y over h dy. And let's evaluate this integral now. So there's certain constants that we can pull out. We can pull out the rho g w, and in doing so, we are left with d minus y times 1 minus y over h inside. And from here, we can simplify further by expanding the inside part, which will give us d minus dy over h minus y plus y squared over h dy. And this is equal to rho GW times dy minus dy squared over 2h minus y squared over 2 plus y3 over 3h. And then evaluate it from 0 to d. We are thus left with rho GW d squared minus d3 over 2h minus d squared over 2 plus d3 over 3h. We can combine like terms, d squared and d3, d squared and d to the power 3. So rho GW times d squared minus d squared over 2 is d squared over 2. D cubed over 2h, negative d cubed over 2h plus d cubed over 3h is negative 3 times d cubed plus 2d cubed over 6h, which is negative d3 over 6h. So see if we solved it correctly. I just discovered a mistake I made. So this equation is lacking a y. So because we had a y over here, but I only plugged in df. So we actually have to multiply this by y. Sorry guys for that mistake. Okay, so let's redo this part. Um, yeah, I was wondering why my answer didn't match up. But yes, so this one will give us integral of 0 to d dy minus dy squared over h minus y squared plus y3 over h, and then dy. This is equal to rho GW times dy squared over 2 minus dy3 over 3h minus y3 over 3 plus y4 over 4h. Evaluated from 0 to d. This is equal to rho GW times d cubed over 2 minus d4 over 3h minus d cubed over 3 plus d to the power 4 over 4h, and then minus 0. So combining like terms now, you have rho GW d cubed over 2 minus d cubed over 3 and negative d to the power 4 over 3h plus d to the power 4 over 4h. So that amounts to d3 over 6 negative minus d4 over 12h. Um, yes, let me double check to see if that is correct and I'll get back to you. That is indeed correct. So don't lose sight of the whole picture though. And what we were trying to solve for is we want to determine the force in terms of the liquid density rho and the acceleration due to gravity g and the liquid depth and the gate height h and the gate width w. And this is the whole reason why we came up with this moment balance equation at the beginning. And this equation will be useful to us now. Basically, it relates the total moment from the hydrostatic pressure of the liquid on the triangular gate surface to this force needed to counteract that moment. So we will set this moment, which is from the hydrostatic pressure, equal to FH. So rho GW times D3 over 6 minus D4 over 12H is equal to FH. And now we can solve for F by dividing both sides by H. And this will give us rho GW times D3 over 6H minus D to the power 4 over 12H squared. And this is equal to our force. Let me double check to see if it's correct. It is indeed correct, so this is our value for the force. I hope that this problem was helpful to you guys in gaining a better understanding of how to relate hydrostatic pressure to moment and the integration associated with this whole process. And don't hesitate to ask me questions in the comments, and I'll be posting these slides in the discussion as well for you guys to browse over. Thank you again for watching, and I hope to see you guys in the future. See you next time.